This is a talk about ordering processes and living systems. Next slide, please. So I want to talk a little bit about chirality, and not in terms of what we see with chiral preference in sugars or in amino acids, but in terms of the mathematics of it a little bit. So what makes something chiral is that a translation, in other words, moving an object from one place to another, or a rotation about an axis, those are not sufficient to transform one form into the other. If you rotate your right hand, you're never gonna get to the same geometry as your left hand. The same is true with these quartz crystals. Next slide, please. So what we have here are just some ball and stick diatomic molecule models. And you can see there are a reflection. You know, one was reflected to get the other, but the reflection isn't necessary. You can translate, in other words, move and rotate, and you'll get the same form. Next slide, please. So with water molecules, again, with a triatomic molecule, reflection is not required. It's not a chiral element. Next slide, please. And then if you have a 4-component molecule, again, it's not going to be chiral. You can see there are 3 different arrangements of a 4-component system, and in all of them, it doesn't require reflection. You can rotate and translate, and you'll get from one to the other. Next slide, please. So with a 5-component system, you have forms that are unique, that are chiral. And I think the reason is strictly geometrical. So if you look, we're in 3-dimensional space, and a 5-component system has 4 edges. So it's one more parameter than the dimensional size of the system. Next slide, please. And so what we have with at least 5 components, you could have a symmetrical system wherein you could have just translations and rotations will get you a chiral element, but you may not if it's not a uniform system. In other words, if you have a different kind of molecule, you won't. And why is this important? So briefly, let me say, with chirality, if you're introducing an enantiomers, what you're introducing is a new state of the system. And so simply by adding an extra atom to a molecule, what's happened is that there's now not just one new state, but there's also a second new state for no extra energy. So in other words, it didn't take any extra, it's just a feature of the geometry. And when you have a lot of states, it's actually really easy then to lower entropy. One of the features of living organisms is that there's a local decrease in entropy. And if it's really easy to create equivalent states, then it's also really easy to have lower entropy. Next slide, please. And so I want to talk a little bit about systems as well. The first 2 things here are probably the most important, that a system has elements and that there are also relationships between the elements. And those relationships serve certain functions. There are feedback loops. The system exists in an environment. There may be a boundary. There may be emergent properties. Next slide, please. So if you look, this is, I think, the Ganges Delta. It's a river system. Some of the elements, you can think about the elements. There's water, there's sediment, there's certain energy in there too. Next slide, please. Here's a storm system. You can think again about the elements. You can think about the water. You can think about the air masses, the energy in the system, the heat. Next slide, please. Here are some sand dunes. Again, you can think about the elements of the system. Are we? Yeah, we're in the same place. Okay. So with sand dunes, some of the elements are the sand and the wind. Next slide, please. And one of the features, so this is a picture of bedded sandstones that are, they're basically preserved sand dune structures. They're aeolian structures. And one of the things you notice here is these unconformities where you have bedding structures, and then there's a nice planar feature, and then there are bedding structures with a different geometry. So what this is evidence, very clear evidence that sometimes systems disintegrate, that they, whatever was holding a system together ended. And this brings about, or this is brought about by some failure of some of the system's functions to maintain itself. Next slide, please. And that implies that there might be some kind of ranking process in the functions of systems. Now, this is important in making a model, in looking at how one might model a system. And if one is looking at the different features of symmetry in a model, that may be a little different from the symmetry that you'd find in an actual physical object, just because the space in your model that you're creating the symmetries in is an abstract space versus say three-dimensional space. So the limits are a little different. Next slide, please. But what's neat is it's not that difficult to create a mathematical terminology for it. So this is an easy example from Wang's paper. The system has attributes and also relations between the attributes. Next slide, please. For a closed system, you can talk about components, relations between the components, functions or behaviors, and also constraints. Next slide, please. For an open system, it's changed a little bit. You still have components, relations between the components, but the relations can be split between internal relations, external input relations, and external output relations. And then the constraints, you also have an environment that has components outside that get used. That's the theta at the end. So next slide, please. What you can do then is you can do some mathematics with it and play with your model space. That's one of the things that I'm planning to do. Next slide, please. But really, I wanted to talk more about how the mathematics interacts with the idea of entropy. This is the statistical definition for entropy. Next slide, please. And we have also the historic thermodynamic definition for entropy. Entropy is just the difference between internal energy and free energy to do work per degree of temperature. So next slide, please. If you take what Boltzmann found and apply it to information entropy, into information. The entropy is really where the thermodynamic entropy had a physical parameter that was measured. Um, uh, the information entropy is more just a model. Stands for probability that that information will occur. And so information entropy is really sort of a measure of how surprising or uncommon certain information is. And it just basically has the same structure as the statistical mechanic entropy that Boltzmann discovered. Next slide, please. You can also talk about species entropy, which is the sum of reductions of entropy in a population compared to free energy in the environment. And you can also talk about the information entropy of the genetics. But really, these are all sort of mathematical rather than empirical. I don't know that people are trying to do work with populations and seeing what the difference between the free energy and the internal energy of the systems are. Sorry. Okay, next slide, please. But basically, people are taking the same equation. And sorry, I forgot the summation sign here. There really should be a summation sign. It's a sum of the probabilities of the different states of the system. And again, let me repeat, the interesting thing about chirality is it's very easy to see that when you get a certain number of parameters that number is larger than the constraint on the space of that system, that you end up with you end up with chirality, and that's really a reflection of having extra states that you wouldn't have had if you hadn't pushed up against the number of dimensions that are there. Next slide, please. So again, if you're looking at a model system that may be different from a physical system, but these exist in a mathematical space or in a geometric space. Okay, next slide, please. So one of the nice things about an ordering function is that it can be used to maintain the stability of a system. But that would only exist in a model like a mathematical model. We don't necessarily see ordering in the way that mathematically we do, unless we have copying and coding. And so that's sort of interesting when it comes to origin of life, because we can do mathematics and physical rearrangements at the same time with genetic systems. Next slide, please. But at its most basic, there's also a drop in entropy in crystals. And this makes sense. And this is an image of a platinum crystal, but it's just here, very easy to see the unit cell and how it repeats. And it's also really easy to think about how each atom, if there was a melt and the crystal was forming and growing, you could easily see that there are equivalent states that an atom could end up at. And so because there are so many possible equivalent states, it's really easy to get a drop in entropy. Next slide, please. With crystals, there are 14 different lattice types based on symmetries. You even have higher dimensional symmetries that you have to model in higher dimensions, but we actually have quasi-crystals that have those higher symmetries, like a five-fold symmetry that exist in nature as well. Next slide, please. And the study of symmetry also has had some great work done, especially recently. The finite simple groups have been all completely described. There are other kinds of finite groups as well. Next slide, please. But the transition to a living system, I think, is what we're all sort of interested in. So next slide, please. And a living system, and maybe one of the important things about a living system is that it arises when that system is part of a population, which is not the case for minerals. In other words, a mineral may not. I mean, even though yes, there are mineral species that exist, minerals aren't reproducing in the same fashion. Next slide, please. Instead, let's look at an example, say geothermal hot springs. Um, Within that, it's really difficult to see how the reproduction might occur. Is there some conservative process that has a lowered entropy for that process that leads to reproduction? Next slide, please. And I want to talk a little bit also about icy worlds hypothesis, which is not one of the more famous ones, but basically it's abiogenesis on an icy world. Some of the benefits of that one are that the RNA is fairly concentrated if it's not in liquid water. So it's concentrated enough to autocatalyze. Another feature of icy world hypothesis that may be good is that ice can produce some electricity when there are tidal forces acting on it. It's not only piezoelectric, it's also paraelectric, meaning that it will have a nonlinear response if there's an electric field. So there's at least some energy that might show up cyclically during tidal forces. There's also a history of icy worlds. There's snowball Earth. There are comets. Other objects in the solar system that have water ice and other kinds of ices. You could get the same kind of delivery to a snowball Earth that you could to geothermal hot springs. So that's interesting. And the nice thing to look at is, are there structures that are going to have lowered entropy that are going to allow for reproduction that's going to allow for a population? Next slide, please. And so the next steps, I'm going to try and create a mathematical model and maybe some scenarios that can be falsified to form the basis of some experiments maybe. Next slide, please. I recently had this article that came out, Finding and Creating a Living Organism, Past and Future Thought Experiments in Astrobiology Related to Artificial Intelligence. And I was looking at some of these same things in this article, so if you want to find more information, you can check this out. Next slide, please. And I wanted to thank Sohanjita and also Martin Dominic and Catherine McGrath. I really am enjoying this conference very much. And that's it for me. Thank you so much. Hopefully you'll have some good questions.